Hello everybody. Last time we started talking about the image filtering. we talked a little bit about it. We will continue and finish up with this topic: filtering, convolution, derivatives. We are going to talk about derivatives a lot because taking the derivative of a function or a discrete function such as an image is important for us. And then we are going to talk a little bit about how to do the convolution with the Opencv and related functions today. Your first homework is out. It is posted on the Teams page. You are going to submit your homework with the Teams program. Okay, this is what we talk about. We said that there are many types of images: binary, grayscale, or color. Usually we will be dealing with grayscale. Binary is too constrained. It is only 1 or 0. Color is very general purpose. Yeah, we can use it for any purpose. But if we solve problems with the grayscale images, it will be applicable for both color and binary images too. So most of the time we will deal with the grayscale images, and we talked about these last time. As I said before, grayscale images are usually remember we said that an image is a matrix, okay, and each matrix element for the grayscale images are usually from 0 to 255. Sometimes we can use, instead of 8 bits, to 16 bits. If it is a 16-bit, then it's going to be 0 to 2 to the power 16, right? Sometimes it is 8-bit, 10 bits. In that case, it's going to be 0 to 1024. So the RGB images, color images, means that there are 3 channels: red channel, green channel, and blue channel. So it's like 3 gray level images, grayscale images stacked up together. So 3 channels. So it is not any different than grayscale images, other than we have more data. We talked about histograms last time. I guess we stopped here, I guess. So we said that the histogram means the meaning of histogram for an image is no different than meaning of the histogram for any statistical data. Usually we take histograms of students' scores, right? We say that for a class we have okay, we have 100 students, and student number 1, 2, 3, 4, 5, 6, etc. We have 100 students, and each student has a grade. Somebody got 98, 31, 57, 61, etc. When I say create a histogram for this class's scores for this exam, you would get something like this, something like that. And usually we show it like a curve. Okay, so that means that this is the mode of the class. That means there are maybe 10 people who got 60. Okay, so if I do the same thing for this whole matrix, there are 100 by 100 image. If there are 10,000 elements of this image, pixels of this image, and each pixel has a score from 0 to 255. If I draw this diagram, I would get something like this. It looks like in this image I am not using values greater than 130. Okay, that's what I am doing. So histogram, we are going to use this from time to time. Okay, and we started talking about, I guess, image noise. We said that you have a camera, and you are looking at a screen. You are looking at a scene, okay, with the camera. Scene is static, camera is not moving, nothing is changing, like your office room, okay. So you take a picture, and it will produce a grayscale image, let's say it produced a 100 by 100 image. There are total of 10,000 pixels. So this is image number 1. Right after the image number 1, I take another image, like 1 second later, I2. Okay, this is 100 by 100. If I take the difference of these two matrices, okay, normally I would expect the results to be 0 because nothing has changed. My camera did not move. My scene did not change. No motion, no lighting changes, etc. Normally you would say that these two images are exactly the same, but it doesn't happen that way. You would see slight variations. Okay, slight variations. What are the slight variations? Most of them come from the camera electronics. Okay, with the camera electronics, they are sensors, basically light sensor, right? And for a given amount of light, they produce a value, but this value changes from time to time just a little bit. Okay, you don't make perfect. You don't make perfect. Measurements with the electronic devices. They make some error. Okay, this error is what we call is noise, image noise. Okay, so you with the images you don't get exactly the real values, but you get the values that are related to real values, but they have errors in it, and these errors are called noise with the images. Okay, and noise is random. We assume it is random, but this randomness follows some distributions most of the time, and most of the time it is very convenient to assume a normal distribution for this random. So usually we add a noise around 0. Okay, sometimes the values come back a little bit smaller than what it needs to be, sometimes a little bit larger than, and the possibility that the measured value is way off from the center is a lot less than the values around 0.0. That's the assumption. Okay, in this case, if IXY, if it is the true pixel value, this additive noise, there are different types of noises. One of them is additive noise. This additive noise is added to each pixel, and this nxy is obtained from a distribution. Right? So IXY plus NXY is our resulting image. So this is what I am expecting. This is the true pixel values, but this is what I am getting. What is the difference? The difference comes from the noise. Camera noise, lighting variations. You will say that the lighting is perfect, but in my room I am using these fluorescent lights. The fluorescent lights, they flicker. Okay, when they flicker, if you take two images one after the other one, the first one and the second one, their light intensities are different. So this is a lighting related noise. Sometimes camera related noise. Sometimes vibrations in the room cause noise, etc. Okay, so this is additive noise, and we are going to look at it. Okay, sometimes we have multiplicative noise. Okay, the noise amount is multiplied by the true image pixels. So this is a more serious, okay, more serious noise type, because you multiply your image pixels with some new values. Okay, with some new values, and what kind of noise we are going to see in this case? Can I see it? No, I am not going to. Okay, so these values are very close to 1.0, so it is very, very similar to the original image, but sometimes these values are 0. You multiply image with 0, so it becomes 0, and sometimes very large values like 255. If I multiply one value with 255, it becomes very bright. sometimes it is 0. So some of these pixels would become completely black, and some of these would become completely white. Blues are white, okay? And we are going to see examples of it. Okay, so let's look at the distributions for the noise. The most widely used additive noise model is Gaussian noise. Okay, this is the Gaussian curve. Again, this is centered around 0. Gaussian noise, this is centered around 0. Good. And this one is called, this one, the here 0 is called the mean of the distribution. It doesn't have to be 0 actually. It could be different. And the width of this curve is related to this parameter sigma, standard deviation. And given these values n and sigma, I have only 2 parameters for this distribution. I can get the distribution for the noise. Okay, remember the true image is I. I think I just did the opposite. I think the true image is I and this is I hat. Okay, so I get the n values from this distribution. Okay, the probability of having 0 or values around 0 is the highest. The probability of having values smaller than 3 or larger than 3 is very, very slim, but it is not 0.
I have a question.
Sure.
We talked about pixel level noise. I mean, the noisy value of pixel is calculated from only related pixels. Is there any noise that's calculated from other pixels? The combination of other pixels.
Well, our noise models for this case is very, very simple. We assume that the noise is independent. Okay, for each pixel there is a new noise, and this noise is taken from this distribution. Okay, so as you see, noise is not dependent on the position in the image, which is not a very realistic assumption, but it makes our calculations a lot easier.
Okay, thank you.
So usually, I mean, remember, I think lens introduces some kind of a noise to our images, especially when you go to the edges of the images, these edges of the images, okay, the corners, your images become darker, they get blurry. That means that the noise depends on the position on the image, right? But no, we don't try to model. Of course, there are ways of modeling it. We don't try to model those kind of pixel dependent, image position dependent noise at this level. But we need to know that noise exists, and whatever you do, you will have to live with noise all the time. And we are trying to model it as simple as we can. Okay, this is one example of Gaussian noise added to this image. It looks like the sigma is very wide in this case. Okay, there is another way of modeling the noise. It is the uniform distribution. You would say that the values between A and B, any value could come, and their probabilities are equal. The probabilities of these values are around 0. 0 is the highest, and when I get away from 0, it drops exponentially. But in this case, any value coming from between A and B is equal. Of course, from 0 to A it is 0, from B to onwards it is 0, but anything from A to B is same. It's called the uniform distribution. Okay, and we have the salt and pepper noise. Again, it's a multiplicative noise. And then I did the same mistake here. Okay, original image multiplied by this salt and pepper noise. With the salt and pepper noise, all you do is you change some of the values to 0 and some of the values to 255. So it is not related to actually what the original image pixel is. Okay, so usually electronic devices cause these kind of problems. Some of the pixels are bad, they are just black. Some of them are all white. This is called salt and pepper noise. Okay, so Gaussian noise, uniform distribution. Gaussian noise, uniform distribution, uniform noise, salt and pepper noise are the three noise types that we are going to look at now. Let's look at some of the techniques that we use to address this noise issue. Okay, image filtering. That we are going to call this process image filtering. Okay, we are going to try to filter out the noise that we have in the images. It's an important step. Okay, it is used for enhancing the images. We denoise it. Okay, when we resize the images, again we try to remove the noise and resize it. We try to increase the contrast. Again, we use this kind of filtering, because when you increase the contrast, you don't want to amplify the noise. What is increasing contrast? How do you define contrast? What is an image contrast? Can you tell me?
The difference between colors. Range.
Yeah, you could say that really. Actually, remember the histogram that I showed you? This histogram shows that the contrast of the image is not that high. Why? Because the difference between the black parts of the image and the white parts of the image could be at most what? It could be at most 130, right? So it is not contrasted. There is no contrast, not much contrast. But if I use the whole range from 0 to 255, then my contrast would have been higher. So when we increase the contrast, so what would you do? How would you? Okay, tell me something. How would you increase the contrast of this image by looking at this histogram? Tell me a simple operation.
Histogram equalization.
Nobody knows what histogram equalization is.
Can do a little bit normalization here. Like,
okay, a little bit normalization. What do you mean by normalization? Just tell me the normalization procedure, but it should be like 5-word normalization. By using 5 words, no, 3 words, you will say that
we can, for example, 50, we can, we know that the range is here 0 to 150. We can, well,
hold on a minute. I have to take this, sorry. Efendim? Ya şu anda dersteyim. Daha sonra görüşebilir miyiz?
Tamam, ne zaman arayalım?
Saat 4.30'da bitecek dersin. 4.30. Teşekkürler. So, yeah, go ahead.
We can map 50 from 0 to 152.
Yeah, but what you are saying is nice, but tell me 3-word or 4-word procedure to increase the contrast. Salman, you said something I did not understand what you said. It is
Until limit theorem, or maybe Gaussian, or I can say also that Gaussian normalization.
maybe a Gaussian normalization could be a good thing, but I was expecting something simpler. Here, what would you do is multiply each pixel by 2. If I multiply each pixel by 2, all the 128s become 255. All the zeros become 0 again, and all the hundreds become 200, right?
Yeah, it's much simpler, yes.
Okay, that's I mean, for this image, obviously it works only for this image, but it works for this. But if I do that, I will amplify the noise that I have in this one. Remember what was the noise? Noise is I plus N. This was my image, right? So if I multiply by this 2 by 2, I am multiplying both the original image and the noise. So I am amplifying the noise. So it will be more visible. Maybe before doing that, before doing this, I should do something, okay? So filtering is important. So we will look at that in a few minutes. Okay, so when we enhancing images, we need to take care of the noise. When we extract information from the images, again, we are going to use these filtering techniques. Okay, for example, finding the edges in the images, finding the corners, or finding the some special points in the images. We are going to use filters, and these filters are going to be very useful for us for both eliminating the noise and finding this kind of stuff. Okay, so before we move to the filters or the convolution operation, let's do some review about the derivatives. Okay, derivative, you know this from high school, even from the primary school maybe. Derivative means that rate of change. Derivative of a function is, for a given point, find me the rate of change of that function. Okay, if you have a function that shows the distance of an object, okay, if this is the time and this is the distance, and if the object is doing this, okay, then derivative of this, okay, derivative of this distance with respect to time is the speed, right? So derivative of so if you find the rate of change, that means that what is the rate of change at this point? It is a tangent, the slope of the tangent line. It is very, very steep, but at this point it is not that steep. It is kind of flatter. So we would say that at green point the speed is higher than the red point here. Okay, so if you take the derivative of the distance function, you would get the speed. If you take the derivative of the speed function, you would get the acceleration. Okay, that's the definition of it. The average, the meaning of average is dividing the sum of n values by n. Okay, if I have a function and if I evaluate all these functions I from 1 to n, so that means that add all the function elements at these discrete points, and if I divide them by n, I would get the average of it. So a very simple review here. Okay, so that was the definition of the derivative, right? So this is the basics of very fundamentals of the calculus. So the calculus. So we are talking about infinitely small values here. If I evaluate this limit, okay, at this point x, so subtract fx value, subtract this x minus delta x f value from fx and divide this by delta x, you would get this slope. Okay, so there are many ways of calculating this. There is a definition of it, and luckily for us, they proved all the theorems, and they came up with nice ways of calculating the derivatives. When they say that if my function is x squared plus 1, they say that we know a way of calculating this. In this case, you are going to do 2x to the power 1 plus, in this case, 0. Okay, so it's going to be, your derivative is going to be 2x. Okay, so you know the details from your calculus classes. Okay, and these are the notations. If I take the derivative of the distance with respect to time, I would get the speed. If I get the derivative of the speed with respect to time, I would get the acceleration. We all know those. But in our world of image processing, computer vision, okay, we don't have nice functions like continuous functions like fx's. Okay, we have discrete functions, and we need to find a derivative of discrete functions in a few minutes. Okay, we already know these. If I have such a function depends on x, if I take the derivative of y with respect to x, I would get that one, 2x plus 4x cubed. Or if I take this one, okay, they showed you how to take the derivative of sine, right? It is cosine x, and we know that derivative of e to the power x is e to the power x again, but I have to take the derivative of the upper side, which is -1. Okay, so good. So these are the analytic derivatives of the continuous closed form functions. But in our case, we live in a discrete world. Okay, in a discrete world, we don't have continuous values. So when we say delta x cannot be as small as possible. Okay, delta x is at the smallest is 1. We cannot go any smaller than 1 because it becomes 0. Remember, in this case, this delta x doesn't become 0. It is very, very close to 0, but it is not 0, right? In our case, with the discrete world, okay, this delta x is either 0 or 1. We don't have any values in between. If it is 0, then it becomes 0 over 0. We don't have anything in our hand. So we have to use 1, unfortunately. If it is 1, then our calculation becomes like that. fx minus 1 over 1. So that would be our derivative. So if you have a function like this, a function, in this case, f0 is 1. Let's say this is 1, 2, this is 1.5, 3, 4, etc. So f0 is 1, f1 is 2, right? f2 is 1.5. It goes like that. Or maybe I should not use any real numbers. Just use 1, 2, 3, 4, and 5. So this is 3 and this is 2. Okay, so in this world, if I need to take the derivative of this function f, then I have to do this. So if I take the derivative of f at point 1, what am I going to do? It's going to be derivative of f at point 1 is f1 minus f0. f1 is 3, f0 is 1, it's going to be 2. Okay, so this is how we take the derivative of discrete values. Okay, I use this one. This is called backward difference. You might say that why did we subtract fx minus 1 from fx? Maybe we could have subtracted fx from fx plus 1. Then that's possible too. That's called forward difference. And there is a central difference. Without evaluating at fx, we evaluate at fx plus 1 and x minus 1. So each one is in a definition, with a definition, the derivative of this discrete function. These are just approximations, right? And our images are approximations of real world light intensities on our matrix. Since we are on a computer, we have to do these kind of approximations. They are not perfect, but if the images are high resolution, the resolutions are high enough, if our sampling rates are good enough, then we will be close to the real world values. Okay, so I think this is a example derivative case. If this is my fx, f0, f1, f2, f3, f4, right? 10, 15, 10, 10, 25, 20, 20, 20, it goes like that. If I take the derivative of f 0, it is, well, can you tell me what this is? 0, where does it come from? Can you tell me where this 5 come from?
It's come from 15 minus 10.
15 minus 10, I know that. How about this 0? Where does this 0 come from?
Because before 10, it's infinity. It's minus infinity.
Well, it is. If it is minus infinity, then why is this 0?
I guess initial condition is 0.
Well, I think it is. It is not defined, because what was the definition of fx? f prime x is fx minus 1, right? So fx is 10, fx minus 1 is, I don't know, no definition. Since it is not definition, I just put a 0 in there. So 5 comes from this one, minus 1, 10 minus 15, 10 minus 10, 25 minus 10. Yeah, okay, it goes like that. And if I take the derivative of the second line again, I get the second derivative of this function. Okay. So this is all taken with the backward difference. Okay. So what is the meaning of this plus minus 1 plus 1? It is this. To evaluate this f1, you multiply, let me use a different color. You multiply minus 1 with 10, and you multiply plus 1 with 15, and you add them. So minus 10 plus 15 is 5. And I do the same thing for all the numbers. Here, let me use the green. Minus 1 times 25 plus 1 times 20. So 25 minus 25 plus 20 is minus 5. Okay, this is where we get the minus 5. Okay, so that's how we apply these two numbers. Actually, these are called derivative masks. It's just 2 numbers or 3 numbers. So I apply these numbers by multiplying with the original data and adding them up. masks. Okay, backward difference mask, forward difference mask, and central difference mask. Central difference mask says that, okay, multiply okay, central difference mask says that multiply this with -1 with this 0 and this 1. So -10, 0 and 10, the total would be 0. So with the central difference derivative mask, f1 would be 0. And again, do the same thing. Just slide these three. Okay. Slide these three to the next spot and multiply 15 with -1 and 10 with 0 and 10 with 1 and add them, so it's going to be -5 for the second one. And do this again.
What about the central difference of F1?
I already did that, right?
No, actually we did for F1, F2.
This is F1.
F1.
You
But,
mean you mean this one?
Yes.
I thought we started with F0. Okay. So again, this is not defined, so I'm going to assume it is going to be 0. Well, with this notation. Of course, there are many ways of dealing with this, and it will come at the end of this lecture today. At the boundaries, what are we going to do? Either you assume 0 or you do other stuff, and we are going to see it. Okay. Let's move on. Okay. Discrete functions are nice for us, but our discrete functions are not one-dimensional functions. Our discrete functions are two-dimensional images. Okay, so if this is my one-dimensional image, I am fine, but my data is two-dimensional, like that. Okay, so I would put these numbers in here: 10, 15, 10, 10, 25, 20, 20, 20, and let's say 30. So it is like a line in my code. So what am I going to do? I will fill in the others: 30, 10, 5, 10, 20. Okay, like that. Okay, so they're all filled in. Okay, so if I like to take the derivative of this image, then I cannot give you a single number anymore, because there is derivative with respect to x dimension and there is derivative with respect to y dimension. Okay, there is not a single derivative value anymore. Okay, there is derivative with respect to x and derivative with respect to y. Well, they define this: if I have a two-dimensional function, okay, then in that case I am going to take partial derivatives, because my function depends on x and y now, not single x and y. So I can take my derivative with respect to x this way. If I take the derivative of this point using the backward difference, okay, it's going to be, let me try to do that. Okay, let's say this is my function I image. Okay, if I take this is how you show it. Let's say this point is what? 1, 2, 3, 1, 2, okay, 3 and 4. I, 3, 4, Okay, if I take the derivative of I34 with respect to x, so that means 20 minus 25 is going to be minus 5, right? But if I take the derivative of this I34 with respect to y, then it's going to be 5 minus 25 is going to be minus 20. So I have two derivatives. That's why we call partial derivative. Partial derivative with respect to x and partial derivative with respect to y. And this is not only for discrete functions. If I have a continuous function, and if I take the derivative of this f with respect to x, I get a number. And if I take a derivative of this function with respect to y, I get another number. If I put these together, okay, I would get a vector now. Okay, two-element vector now. So, derivative of this function with x and y, with respect to x and y, would form a two-element vector, and we call this a gradient vector. Okay, gradient vector. If this function is three-dimensional, then our gradient vector is a three-dimensional. Okay, and as you know, we have three-dimensional images, right? Like the medical images, MRI images. Okay, with the gradient, we define two more things. One is the gradient magnitude, which is the geometric mean of the two values, fx squared plus fy squared. You sum them up and take the square root. This is called the gradient magnitude. And then the gradient direction is the angle between these two. I mean, if I take these fx and fy as the two sides of a triangle, then this is the angle between them. Fx over xy and inverse of tangent. It is something like this. Okay. Let's say these are positive, doesn't matter. This is fx and this is fy. This is a, okay, triangle, and this is that angle here. Okay, and that angle is the gradient angle, and this distance is the gradient magnitude. Okay, this is, we know that, right? This is fx squared plus fy squared. These are some definitions that we are going to use in a while when we do the edge detection, corner detection, etc. Okay, any questions so far? Any questions? Okay, so again, I gave you some definitions, but these definitions are all defined on the taking the derivatives of the images. Remember where we started? We started from image filtering and noise removal and etc. And before we went on, we take a side step, and we reviewed our gradients and taking derivatives of continuous functions, but especially we are more interested in taking the derivatives of discrete functions and images especially. Okay, so for two-dimensional images, these are going to be our derivative masks, at least as an example. I can show you this. Remember my backward difference derivative mask for this one? It was -1 +1. I multiply 10 with -1, 15 with +1, and I add them up. Okay, so 15 minus 10 is 5. how are we going to do this in two-dimensional world? One way of, and also, there is no single way of calculating this derivative. I defined 3 ways of it. There would be even more, but I am not going to do that. I will try to do the same thing with the two-dimensional images. Since it is two-dimensional, there is not a single derivative anymore. There is the derivative with respect to x and derivative with respect to y, and these are the derivative masks. So how is that going to work? It's going to work like this. Multiply 10 with minus 1 plus 10 with 0 plus 20 with 1, and then 10 with minus 1 again. You understand it, right? Let me try to use a different color for the second row. 10 with minus 1, 10 with 0, and 20 with 1. You get the idea. So what would be the result? The result would be for this position. What is the result? You tell me.
0.
No.
Pardon.
No.
30.
It is 30y because these are all multiplied by tens, and then minus 10 plus 20 is 10, and 10 and 10. It is 30, but don't forget about this 1 over 3 at the beginning. So it's going to be 30 over 3. It is 10, right? It's going to be 10. So let me try to write a matrix here. It's going to be 10 for this position, and I cannot calculate it for this position or this position or that position. So I am going to fill in zeros here. 0, 0, 0, 0, 0, 0, 0. How many rows are there? Okay, 5, right? 1, 2, 3, 4, 1, 2, right? Okay, so 10 here. How about this position? What would I get?
Okay.
It's going to be
10 again.
10 again, right? Because 20 minus 10, 20 minus 10, 20 minus 10 over 3 again. How about this position?
0.
It's going to be 0. Why? Because they are all the same. Okay, you get the idea. I think we are going to get the exact same thing, right? 10, 10, 0, 10, 10, 0. So for this matrix, if I use this derivative mask for fx, I will get these values. Okay, so this is for fx. How about fy? Let's write the fy. Fy is going to be, for this position, calculated
0, all of them, I think.
these are all 10. 10 minus 10, 0. 10 minus 10, 0. 20 minus 20, 0. These will be calculated by zeros. I think it's going to be all 0.
All 0, yeah.
It's going to be all 0. 5 zeros. 1, 2, 3, 4, 5. It's going to be all 0. So remember, what was the definition of derivative? Rate of change, right? So if I move in y direction, either up or down, doesn't matter what column I am at, the rate of change is always 0 because nothing is changing. It is all 20s. It is all 20s. It is all 10s, right? So derivative with respect to y direction is always 0. But if I move like that, so what I would see is at the beginning it is 0, then there is an increase, then again 0 again, right? So it is moving a little bit up, and then it's becoming 0 again. So with respect to x, there is a change, and I can detect it. With respect to y, there is no change. Okay, so it works. The definition of derivative, I can do it with these derivative masks. Okay, any questions? Okay, if there are no questions, then I will take 10 minutes of break. We will be back at 33. Okay, 14:33. Ben derse devam ediyorum hocam. Okay, so I think the calculation is done by these slides. So when we calculated this Ix, did I say this? Oh, okay, what I did was wrong. This should be Ix and If. Ix and I, because fx is already used by these masks. Okay. So this is Ix and this is complete Ix. This is how it is calculated. And this is the whole thing, yeah. Okay. This is Iy. This process is actually what we are doing here is a convolution. Okay. With the convolution, you take your mask, okay, you place it around, let's say, around this red rectangle. Where is, yeah, okay. You take this mask, you place it around this red rectangle, you calculate the value and you place it in here. And then you move your mask to this blue position and you calculate the value, do all the multiplications and additions, and you put the resulting value in the respective position and you get this 10 and you continue. Okay, this is called convolution. Okay, and it is denoted with this asterisk sign, convolution. And doesn't matter if this is your image or the kernel or the mask. Okay, in this case H is the kernel, F is the image. So there is a two-dimensional, there is a two nested loops, okay, K and L for each dimension, and this one only calculates a value for a pixel only. Okay, this is called the convolution operation, and we are going to show it with this sign. We are going to convolute this I with fx. That's going to give me the derivative with respect along the extraction, and when we do it with the fy, we are going to get it for the y direction. Okay, so convolution is something that we use a lot. It's a linear operation. There are many features of it that we like. For example, convolution is associative. Doesn't matter if you have three matrices like these. Doesn't matter if you do the convolution like this first and then next, or first this one and then next. So it is associative. Very nice property that we are going to use this a lot. Okay, so the convolution associative, we know this one. Okay, I already talked about this averaging stuff, and let's try to talk about this Gauss distribution, and let's try to formalize this Gauss distribution, filtering with Gauss distribution with the convolution. Okay, so remember, let's go back to the single dimensional functions, back to single dimensional functions. This is a Gaussian function. This is a continuous function, but we live in a discretized world. And if I use a discretized mask for the Gaussian function, I would get this. At the beginning, at the center, I have 1. Then it's a symmetric thing. You see, it's a symmetric 1, 0.6, 0.6, and it is getting smaller and smaller after a while. It is all 0, I assume. Well, in reality, it is never 0, okay? But these are very close to 0 here and here, till the infinity, minus infinity plus infinity. Okay, these are very close to 0, but it's not 0. But in discrete world, I assume that after a few steps, it is all 0. Okay, it is all 0. So if I take this as a mask, okay, remember I did the similar stuff with one-dimensional image. Okay, so derivative mask, it used -1 plus 1. Center difference is used -1, 0, 1. With the Gaussian mask, I am going to use all those values. Okay, I am going to use all those values. Where are those values? These are the values. There are 7 values here. I am going to convolute my one-dimensional function with these values. Okay, and that's going to give us some effect. Okay, good. So we like Gaussian a lot as a filter. It is useful for many things. Okay, we call it most common natural model. It is good for many types of noise. Okay, and since it is based on this E, okay, taking derivative of it very easy, because e to the power something is e to the power something, right? Of course, you need to take this. Remember this. If you take the derivative of this upper side, it is 2x, right? You are going to get the 2x, and there will be some cancellation out because there are 2's here too. Okay, so we will, by the way, this is sigma. Why, I don't know why it doesn't show it, but this is sigma square. Okay, so there are many things that we like. Most common natural model, it has infinite number of derivatives. You can keep taking the derivatives. It's not going to go away. It's not going to become 0. Okay, it is symmetric. That's good. Okay, Fourier transform, I didn't talk about it, but in the frequency world, going to the frequency world, Gaussian stays as Gaussian. Okay, convolution of a Gaussian with itself is a Gaussian again. So we are going to talk about this in a few minutes maybe. And Gaussian is separable. What is separable? It is this. Remember, remember we have 2-dimensional. For example, this is a 2-dimensional Gaussian here, or 3-dimensional Gaussian, 1-dimensional Gaussian, 2-dimensional Gaussian. There are ways of calculating this Gaussian by running several 1-dimensional Gaussians. That's what we call separability. Okay, and maybe the most importantly, human eye. Remember I showed you the human retina. Do you remember how many optic cables are going from the retina to the brain? We have our eye here. This is the lens, and this is the retina. I think there is a the blank disc, the blind spot. All the cables are coming out of this hole, and it is going to your brain. This is your brain.
3.
How many cables are there? 3 is no. If you have 3 cables, you are in trouble now. How many cables are there? The thing is, it is not important how many cables are there. There is 1 million. 1 million optic cables are going from your from retina to the human brain, but there are several orders of more light sensitive cells, like 3-4 million. 3-4 million. Okay, so number of light sensitive cells is more. Okay, so what happens to this data? I mean, I have 4 times more data, but there is only just 1 million cables are going. So there is some processing going on at this field, and that process people have found it is some kind of a Gaussian filtering. Okay, so there is a biological motivation for using this Gaussian. That's why we say it is most common natural model. Okay, but mostly we like it because it is symmetric. You can take the derivatives of it very easily, and the frequency transform part of it is again a Gaussian itself. It's very useful. So we are going to look at the Gaussian a lot. Okay, filtering again is convoluting an image with a kernel, with a mask. Okay, you take this image, you convolve it, and you get you come up with a number. Okay, if this is image, if this is the kernel, convolution means that 1 times 1 plus 0 times 3 plus minus 1 times 0 plus, if you do the arithmetic, you are going to get 5 here. Okay, and depending on the kernel definition, you will get some kind of a result. Sometimes these kernels are for taking derivatives. Sometimes these kernels are taking average. Sometimes these kernels are smoothing your image, getting rid of the details or the noise. And you can use these derivatives for many other purposes, and we are going to see them. Okay, here's one example. This is my image, 100 by 100 image. I am convoluting this image with this matrix, with this mask, with this filter. So what did I get?
Same image.
It is exactly the same image. Why? Because it is multiplying each pixel by 1, and it is multiplying the neighboring pixels by 0. So it should be exactly the same. It is the same image, right? That's true. So this is a not very useful, but useful to know filter. How about this one? What does it do?
Shift, I guess.
How does it work? So take this one for example. Let's say I have 3 pixels here. Okay. I have 3 pixels. It says that multiply these with all zeros, but this one. So it's going to take the pixel on my right, and it is going to assign it on my left. So I am shifting the whole image to the. I am going to move the whole image to the left. I think this is wrong, right? I think the black part should be around here, right? This part should be, there should be 1 pixel on the right missing. So this is not correct. So let's make this correct. To make this correct, so let's make this 1. This is 1, and this is 0. So my image is now shifted to the right. Am I correct? Am I correct?
Yes, now we put right, left hand side to center.
Yeah.
So it shifted left.
So the original slide was bad. So I fixed it. Okay. So good. So this was one identity. This one is shifting the image to the right. Not very useful, but again, to understand what's going on, it's useful. That's good. How about this one? What did it do?
Average.
It takes average of 9 pixels in a neighborhood. Okay. Let's say here. Let's take this part. Let's say I have 3 pixels here. Can I make it as large as? No, I cannot. This, okay. Let's say I have 3 by 3 image here. Okay. I am going to add all these pixels and add them together and divide them by 9 and put them in my new image. As you see, the new image is blurred, right? I see the eyes, and there is a single pixel here, this blue here. I can see some kind of a sparkle in the eye, but here I don't see that sparkle anymore. It's gone. Image is smoothed out. Okay, and as you see, this is a constant window, right? This is just a wall. I would expect the values of these pixels, the wall pixels, to be the same, or at least I would expect a gradual darkening right here, right? But some of the pixels are behaving randomly. Do you see that? Some of the pixels are behaving kind of randomly. It is not, you don't see very nice gradual decrease in the wall section. But in the smoothed version, as you see, it is much smoother. So it is the brightest here, and gradually it becomes darker. So I get rid of the noise. Did you see that? I get rid of the noise. Okay, so it got rid of all the details in the what is this? Is this hair? Oh, yeah, whatever. Okay, it's her accessory. I got rid of these kind of details. Like there is a thread, right? This is a thread. This is a thread. So they are gone. I don't think that. Yeah, they are all gone. I don't see them. I get rid of the details, which is a bad thing, but also I get rid of the noise at the upper part. So this is called averaging filter. An averaging filter is good for taking care of some noise. It is not the perfect noise elimination way, but again, it works out to some point. What is this? Why do I have 1/9 in front of this matrix?
We sum 9 elements, 9 pixel elements, so we have to divide it the elements.
Well, if I don't have this 1/9, it wouldn't take the average, but would it still smooth out the noise if I don't put 1/9?
It will be a brighter image.
Much brighter, right? Because you are adding all the pixels around it. It will smooth out the error, but it will be much brighter, and we don't want that. We like to keep the average brightness of two images the same.
And some pixel can exceed the maximum value of
Yeah, yeah. At the bright positions, okay, our resulting value will be higher than 255, and it will be a problem to store those kind of images. Okay, good. So this is a filtering example. How about this one? This is a 5 by 5 kernel now. I applied it. Now this is a larger kernel. What is the effect? It is even has a more pronounced smoothing effect. Right? So if I look at it, our walls are much, the intensity of the walls are much more smoothly changing now. And all the details about the accessories and the threads are gone. I almost lost the eye, right? So if you use a larger kernel, smoothing effect becomes larger. Okay? How about this one? So they have taken the numbers of this filter from a Gaussian, two-dimensional Gaussian. Remember? Gaussian, where is my Gaussian? Gaussian is here. So if I take the numbers from the Gaussian, this is a single-dimensional Gaussian. Okay? If I take the two-dimensional Gaussian, like this, like do this, 0.6, 0.13, and 0.11, 0.6, as you understand, right? So by going away from the center, it's going to drop. And if I do that, what is the effect? Effect is again smoothing. It smooths the image, but this one has a better behavior than the averaging filter, like this one. Can you tell me why would you prefer such a 5 by 5 matrix over this one? This is more preferable in terms of filtering than this one. Can you tell me why?
Maybe further pixels effects less than closer ones.
So what is the advantage of having the closer ones have more effect on the resulting image?
Usually closer ones is much more
Relevant, right?
Yes.
They are much more relevant. Yeah, that's true. That's one thing. Can you tell me anything else that you may prefer this filter, Gaussian filter, than the averaging filter?
Brightness, maybe.
Well, they are both the same. I mean, they don't change the overall brightness. It is exactly the same overall brightness, because the total of this filter is 1.0 and the total of this filter is 1.0.
First filter change uh, 25 pixels, but Gaussian filter does not change all of them. It changes near the center.
No. Well, this filter doesn't change all 25 of them. This changes just single convolution step, changes the single center pixels only. Because I am running the same convolution operation.
Gaussian filters distributed the average to neighboring pixels with a weight.
Well, a few minutes ago somebody said that, right, already. It says that it gives more weight to the closer, more relevant pixels.
Noise is more like is less like to be occurred on center. I think because when we measure the closest point should be like the more accurate point. So
Again, Selman, you are saying the same thing. You are saying that this has the nice property of giving more weight to the closer ones.
no, I'm saying that giving more weight to the closer ones gives maybe a better noise filtering.
Yeah, that's true. So it is the Gauss filter that gives more weight to the nearby ones. It is good for accuracy. It is for good noise suppression. I am talking about something else.
Okay.
It is rotational symmetric. This one is not rotational symmetric. It is not symmetric around this one. Okay, it is not symmetric around one. If you rotate this 30 degrees to the left, it becomes a different thing, right? This one is not like that. Okay, if I rotate this 30 degrees to the left, to the right, it will give me exactly the same thing, exactly the same result. This one doesn't work it that way. Usually we don't rotate our kernels, but we rotate our images. If the image is rotated like 25 degrees to the left, right, I should be able to get the same result. With these kind of stuff, the corners are, so it is more pixelized. As you see, there are some pixel effects in this one. With the Gaussian, this is less. Okay. Well, of course, we are living in a discretized world, and pixelization will happen. With the Gaussian, it will not happen. Okay, so we like Gaussian better. Okay, so this is Gaussian smoothing, and this is smoothing by averaging, and we talked about those results. Of course, with any kind of smoothing, you are going to lose detail. Also, with any kind of smoothing, you are going to lose some noise. Okay, but while losing the noise, we should be careful about not losing the details. And Gaussian smoothing is one of the best ways of achieving that. I am not saying that we are not going to lose any. I am not saying that we are not going to lose any details. Of course, we are going to lose it, but it will be controlled. Okay. This is a noise added image, artificially added. Okay. Somebody has added Gaussian noise on it. Okay. So it's a very bad image now. If I try to get rid of the noise by averaging, I get this. If I try to get the noise by Gaussian filtering, I get this. So this one keeps the details better. Okay, so I think we already did that image filtering. This is how we are doing this. If this is my image, and if this is my filter, okay, the convolution operation will apply this box to all the possible positions, and I will get the results out. Okay, for this one the result is 0. Okay, for this one the result is 10. Why? Because there is this 9 in here. And if we continue, this is what we are going to get. You see the effect? Do you see the effect? So in this case, this is not a binary image. There are zeros, there are 19s, and this is 92. Okay. And if I apply this averaging filter on this one, as you see around here, I didn't define anything. I didn't fill any zeros in there. But you see the effect of this 90 around here. Just make this slightly brighter. But the brightest parts are there because there is no zeros, and this filter is as 3 by 3. So it became like that. If you look at this picture from a distance, this one became like that. Okay, so the box filter, this is called the box filter. It replaces each pixel with an average of its neighborhood and achieves smoothing effect, and it removes sharp features. This is gone. See, you don't see this 90 anymore. It is gone. It is distributed over. It is averaged out. Also the center 0, it is gone, but it made this effect by darkening this 30 here. Okay, so somebody has applied this box filter to this image, and I get this. Okay, I already did that. If I apply this one to this one, what will I get? Of course, the image itself. I know that one. If I apply this one to this one, so what would I get? I'm asking the same question. We already did it.
It's shifted left side.
It is going to shift to the left. Yeah, this time they did it right. Okay, shift left by 1 pixel. Okay, that's good. How about this one? That's a very weird filter. So it multiplies the center pixel by 2. By multiplying it by 2, remember what are we doing? We are increasing the contrast, right? We are increasing the contrast, and I take out the average of it. What kind of a weird stuff is this? So I think it's going to be like this. Multiplication, yeah, okay. So convolution, first convolute it with times 2, increase the contrast, then take out the smoothed versions of it. How does it work? This one is smooth, this one is same image but twice the contrast.
Some of them, I think, can be like a intelligent.
Selman, your voice is so weak. I don't know. Just keep your mouth closer to your microphone. Okay, say it.
Maybe it is like a Gaussian filter, because the center is high and the sides are low. But the Gaussian filter, but the mean is kind of more low, maybe, or more high. I'm not sure.
Well, this is a box filter. There is no Gaussianness, but with even if I replace it with the Gaussian, the effect would be the same. Can we let's say let's do this. Let's say I have this as a single dimensional image, okay? So by this I mean like that, okay? So it is one dimensional image. Let me put some values in there. So it is 1, 2, 1, 2. Then suddenly it is 10, 11, 10, 11, 13 maybe. See, it is very small values, but there is a variation. Then some large values, but again there is variation too. This one says that multiply it with 2. Okay, if I multiply this with 2, okay, what would I get? I would get something like, no, let me make it a little bit like that and like that, right? Then take the smoothed version of it from this image. So what is the smoothed version of this one? This is 2 times this, okay? This is 2 multiplication, this is 2 multiplication, and this one is going to be like that and that, right? Is that true? If I subtract this one from this one, what would I get? I am going to subtract this one from this one. So it's going to be something, it's going to be something, this minus 1, kind of smooth, but when I come here, it's going to be like that and smooth. Something like this. Of course, there are variations here. Let me try to do this again, like that, that, and that. Something like this. What happened? Let me show you the result. This is what happens. Do you see the effect? What kind of effect do I get?
We a better after a better histogram distribution, and
Well, it didn't change the histogram because remember, note that filter sums to 1. So the total of this one is 1. This is 2. 2 minus 1 is 1. So the total contrast is not going to change. So the total brightness is the same. Total brightness. So what happened? It is more sharper. Why? Because the difference between this bright spot and the dark spot, it is more, right? Human eye, for some reason, likes these kind of situations, okay? If I am going to jump from this low position to high position, it likes to go well below the average here, and it likes to go well above that average. So it likes to do that kind of a jump, okay? So this is called the sharpening filter. So the images look more sharper. So accentuates differences with local average. Accentuates the differences with local average. So this is called sharpening filter. The nice thing is if I do this, okay, do the subtraction and come up with a, how do you do the subtraction? It is 0 minus 1 over 9, right? So it is going to be minus 1 over 9, minus 1 over 9, minus 1 over 9, and at the center is going to be 1.1, right? Is that true? Yeah, that's true. So other than the center, they are all going to be minus 1 over 9. And I am convoluting my image with this single matrix. Instead of convoluting with this one, then subtracting the convolution of this one, I am just convoluting with this matrix because of the distribution property of the convolution operation. Okay? So with the convolution, it is like this. I times f plus h is same as I f I h. So instead of doing this constant convolution 2 times, I do this addition. I did it once. Okay, so convoluting with a Gaussian, so our kernel is a Gaussian, has this effect again, smoothing effect. With the box filter, it is harsher. Okay. What else? What else? So these are the other things. Linearity. Okay. Linearity means that if I apply a filter to f1 plus f2, it is the same as filter f1 plus filter f2. That's what I said in a few minutes ago. And shift invariance again. Doesn't matter if I shift my image left or right and apply the filter, or apply the filter and shift the image left and right. Doesn't matter. It's the same thing. Okay. So linearity, shift invariance are some of the properties of linear filters. More properties again. It is commutative. Doesn't matter A times B or B times A. No difference. Associativity. A convolution, B convolution, C is the same as this. Okay. So if I have an image and I like to apply filter 1 and after that filter 2 to that image. Instead of doing that, people usually calculate a new filter F3 and they usually apply this to I. That will make things a lot more efficient. And distribution over addition, again, this is what I said a few minutes ago. And if I have a scalar like that, doesn't matter if you multiply your scalar with the images or the kernels before the convolution or after the convolution. Okay, and we already know that. Input, impulse, identity. Okay, good. So these are convolution. And there is a very fast algorithms for the convolution. Convolution is an expensive operation. It's n square if you do it straightforward way. But there are ways to do it in n log n time. And I'm not going to talk much about it. And Opencv implements many convolution functions. And we are going to look at it in a few minutes. Median filter. Okay, let's talk about non-linear filters a little bit. Okay, median filter is an example of a non-linear filter because median filter cannot be implemented with the convolution. Median filter is this. Let's go back to this image. Okay, or let's go back to this image. Okay, here what I do is I multiply each of these numbers with these numbers and add them up and put the results in here. Median filter doesn't do that. Median filter does this. It takes these 9 numbers, okay, 9 numbers. It sorts them. How do you sort them? Just sort it from 0, 0, 0, 0, 0, 0, 0, 90 and 90. I just sorted them and I take the median number. Median number is 0. Okay, so I took the median number as 0. So it is sorting and taking the median number, ortancı in Turkish. This is called median filtering. Okay, let's try to do the median filtering on this image. So what is the median value of this red square?
0.
It is 0. Okay, how about this one? How about the green one? What is the median value of, let's not use the red color, let's use the green. What is the median value of this?
Again.
What is the median value of this green?
0.
Yeah, 0, exactly 0. How about this one?
0.
0. So it is all the way to the end, it is 0, right? So let's move this here. What is the median of this part here? It is 0 again. How about this one? Again 0, right? Interesting things happening right now. Okay, how about this one? 1, 2, 3, right here, right? No, here. How about what is this? Is it 90? No.
Yes.
No,
45.
0.
0.
Let me try it like that. It is 0 again, right?
0, 4, 90.
How many? There are 5 zeros and 4 90s, so it is 0 again, right? How about now? How about now? It is 90 now, right? Is that correct?
Yes.
Yeah.
So it is 90. If I move it like that, 90 again, 90, and it looks like here this one is 0. Is that correct? This is 0, 0. Okay, good. And in the third row is going to be 0, 0, 0, maybe 90, 90, 90. But the idea is this. Let's look at this one. What is the median value of this one? This one.
90.
90, right? So it's going to be 90 again. So how about the median value of this one?
0.
0. So what I am saying is it will ignore these kind of effects, like if there is a accidentally changed pixel like this, it will ignore it, because 90 will not cancel out, or 90 will not here 90 will not cancel out or average out any 0 values, because that 90 will be ignored here, 0 will be ignored there. Okay, so median filtering is very interesting because it doesn't use averaging, it doesn't use Gaussian averaging or the box filter averaging. It just says that this is an outlier, this is an outlier. So sometimes this is very effective, but median filtering is not a linear filter. Okay, it cannot be implemented using convolution. You have to write a sorting algorithm every time you make a sort, and you get your result and you put it in there. So it is more expensive than the other filters. Okay, but still it is a very effective noise eliminator if you have a salt and pepper noise in your system, especially. Okay, median filter. Okay, here is an example. So this is a salt and pepper noise. Salt and pepper noise means that some of the pixels are accidentally white, some of them are black. See, you see lots of white pixels. If you do the median filtering on this is what you get. If you get the Gaussian filter, this is what you get. If you do the median filtering, it is much better than the others. Okay, and the median filtering doesn't smooth the edges. See, it is sharper. This one smooths out the edges. Edges are all smoothed. Okay, but again, median filtering is not a linear operation. If it is not a linear operation, then I cannot say any of these, and these are very powerful stuff for me. Anyway, but whenever it is needed, you can use the median filtering. Okay, are there any questions? Are there any questions? If there are no questions, let's give 10 minutes of break. Let's take 10 minutes of break. We will be here around 15:35. Okay, people. Okay, people. Let's continue. We talked about the median filter. Is a median filter kind of a convolution? No, it is not, unfortunately. But we like median filters a lot. When it works very well. And we did the comparison. One of the questions that comes to mind when we talk about the filters is the size of the filter. Okay. How large should be the size of the filter, and is it 3 by 3 or 4 by 5 by? Usually we choose our filters with the odd sizes like 3, 5, 7, etc. But how about the difference between them? So smaller the filter, less the effect of it on the final image. That's what we know. But what is the optimal filter size? We don't know. It depends on the application. Also, what are we gonna do with the end of the images, near the edges of the images? So at the beginning I put zeros in there because I couldn't define it, and sometimes people don't calculate it, so images become smaller. Okay, so what are we gonna do about the near the edges of the images when it comes to filtering? Also, with the Gaussian, people usually have this rule of thumb. There is no theoretical justification for this, but if I have set the filter half width to about 3 sigma, okay? So if my sigma value is 1, 3 sigma is 3, so it should be half of the window width should be 3. So of course 3 plus 3 is 6, but I don't like 6 by 6 filters, so it's going to be 7 by 7. So first make a decision on your sigma. Sigma is the amount of smoothing that you're going to apply, and after that make your filter size like that. Okay, but this only applies for the Gaussian smoothing. How about the box filtering? Again, it is up to you. So let's look at this. Let's look at this positions around the edges of the image. What are we gonna do? There are 1, 2, 3, 4, 5 ways of handling this. Okay, so first I can clip the filter. That means that if I apply, let's say this is 100 by 100, and I am going to apply 7 by 7 filter to it, and I like to use this clip filter approach. That's the black. I'm not going to define it. So around the image I left these positions undefined. So in an effect I am making my image smaller, right? So how much smaller it's going to be? If it is 7 by 7 filter and my image is 100 by 100, what would be the final image size? What would be the size of these black regions? So let's put at the corner 7 by 7, 1 like that, right? 1, 2, 3, 4, 5, 6, 7, yeah. So same idea. If I put it in there, I think the center is going to be okay, like this and that. Okay, so for this position I should be fine. 1, 2, 3, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Oh, I made it 8 for some reason. Let me take one out. Take this one out. Okay. 1, 2, 3. Okay, this is the center. So how many pixels am I clipping from the upper part of the image and the lower part of the image and left and right? How many pixels did I... how many rows are there? How many rows are there in my black region? You guys are hearing me? Nobody's answering me.
Yes, I'm here. We have a 7 by 7 filter. So it has to be three squares.
Yes, exactly. So the size here is 3 by 3, right? So I am going to ignore 3 rows and 3 columns here, right? 3 columns. So my image is going to be smaller by 3 from each side. So it's going to be, instead of 100 by 100, it's going to be 93 by 93. Is that correct? No, 94 by 94. So my image is now 94 by 94 instead of 100 by 100 because I clipped it. So this is okay because I just lose a small part of my image. But if I keep applying many other filters, so my image is going to be smaller and smaller every time, and that's not going to be good. So, but it's an option. This is called the clip filter. Okay, so what else other than the clip filter? Okay, other than the clip filter, I have the wraparound. Wraparound filter does this. Do you see what it does? Wraparound. It assumes that after the last line of the image, the first line starts again. Remember, this first line is here. Okay, after the last line, the first line starts again. After the last column, the first column starts again. Okay, before the first line, there is the last line, and it goes like that. This is called wrap around. This is like your image is wrapped around a cylinder or a sphere. That's the assumption. So when you place your 5 by 5, let's say this is 5 by 5, when you place your 5 by 5 filter at this position, so all the pixels are defined, so you don't have to ignore anything. This is called wraparound filter. Okay, and this is the effect. They applied smoothing filter using the wrap around technique. Okay, this is the second one. The third one is copy edge. Copy edge is this. You understand what it is, right? It just copies the last line for several times, or the first line several times, last column or the first column several times. This is the copy edge. It just copies the first and last lines and columns. And this is the final effect. Okay, good. And the final is the reflect across edge. Reflect across edge, you understand what is going on? This is the kind of mirror effect. This is the center, okay? And I do the same thing here too. These green lines that I am drawing are the original last and first lines and columns. And I am doing the mirror effect. I copy pixels from this part to this part. Okay, this is called reflect across edge. And it works very good. Okay, and this would be the final result. So the edges or the near the borders of the images are always problematic, but we have some solutions for them. You don't have to think too seriously about them. Okay, these are the stuff. So these slides, I don't know where I got them. They are talking about the filtering operations with MATLAB, but I'm going to show it with the Opencv. But yesterday I forgot to include some other material from some other source. I'm going to show it to you right now. This is a, come on, get rid of this one. Okay, so this is a nice filter. Now I'm not going to use my pen anymore. Yeah, okay. This is a Sobel filter, and if the input is this is the output. All it does is actually it is taking the derivative, right? It is taking the derivative, but it is taking derivative with respect to x axis. So it is vertical edge. Okay. By the way, it is the absolute value, because sometimes the result of this operator is minus negative, sometimes the positive. It is taking the absolute value. This is good, right? Okay. So if I make this a little bit larger, you see if there is a strong vertical edge, I find it, but it doesn't respond anywhere around here. I cannot, okay, anywhere around here, right? So there is a strong edge there. See, there is an edge, but it doesn't respond. Why? Because this edge is a horizontal edge.
Can I ask something?
Sure.
If we take the absolute value, isn't linearity gone? Because when we have a result, it might be coming from a negative value.
Yeah. Well, this is just for visualization purposes only. Taking the absolute value is not a linear thing, because, I mean, it is not easy to show negative values, but I'm going to show it in a few minutes. They preferred not showing the negative values, but showing the absolute values only, just to show the effect. So this is a Sobel operator. Somebody had invented this for edge detection, and we are going to do the edge detection in our next chapter. Okay, good. So, and this is the horizontal edge. See, I am just showing them one by one. This is vertical, this is horizontal, and I change my Sobel filter this way, just 90-degree rotation. Now look at the edges of the short. Okay, now I am responding to the horizontal edges, and I am getting horizontal edge here. Look at the eyes. So with the eyes, I get response from the eyebrows with the horizontal edges, but now I don't get the response from the eyebrows anymore. Okay, so we are going to use these kind of filters for doing the edge detection. Okay, we already did that. Everybody's using this. Oh, okay, this one is applying the sharpness filter, sharpening filter. Well, it doesn't always, it just more contrasty, it looks more contrasty, but it doesn't always look very good. Okay, so this is sharpening filter. I am going to skip these, and I think I was going to show you some examples here. Where is, yeah, This is Sobel. Yeah, okay, good. Exercise. What is the convolution B?
Gaussian.
You know, you need to give me a number. A, B, C, D, E, F, G, H. The convolution B.
C. Maybe.
The result is C. No, the C is a Gaussian. If I convolute this D with B, what would I get?
Okay.
It's G.
Yes, exactly. See, what is G? G is a output of the convolution B. So what is B? B is kind of a vertical, horizontal edge detector, right? So it is sensitive to the shadows around here. So I get the result around there, right? So it is G. So the answer for this one is G. How about what is A? What is the how do you get A using the convolution operator between any of these images? How do you get A by convoluting an image with another one? Tell me, what should I put in here? A, B, C, D, F, G, H.
C with B.
C with what?
C with B.
C with Bravo, right? Charlie with Bravo. So C with B. If I convolute this Gaussian with this one, I would get A. So what does C do? If I apply C to D, it would do what? It would do blurring, right? If I apply B to D, it would do the edge detection, kind of. Is that correct? Yes. But if I apply A to D, what does it do? If I apply A to D, if I apply A to D, what would I get?
It's the same as
Same as G, right? But it would more effect. It would first smooth the image, then take the derivative, right? Take the derivative with respect to y. So instead of applying two different operations, I would apply just A. Okay, good. How about this one? F is equal to D convolution what? F is equal to D convolution. What is F? Okay, let me show you. Do you see the difference between these two? It is shifted. Right? It is shifted. So F is equal to D convolution, I guess E, right? So it is shifted to the left. How about D? What would you get if you convolute D with D?
D again, maybe?
No. How does it work? I mean, how could it be D again? You are convoluting D with D. This is called autocorrelation, autoconvolution. If you convolute an image with itself, At the center, it would be the maximum.
Is it I?
Yes, it is exactly I. Because convolution actually, it kind of finds how similar the images are, okay? How similar the images are. And if you convolute D with D itself, you would get I. How about this one? If you convolute C with itself, C convolution C, what would you get?
C again.
Why? Because that's one of the properties of Gaussian, right? That's one of the properties of Gaussian. Exactly. That's one of the properties of Gaussian. Good. Okay. So, do I have anything on these slides that I like to? Okay. So, this is good. I already talked about it. Correlation and nonlinear filters. Yeah. This is median filter. This is an image, salt and pepper. If you apply mean filter, it's not going to improve the results a lot. But if you apply very mean filter, not going to be okay. If you apply 3 by 3 median, okay, you get this. If you apply this one with 11 by 11 too much, you get the posterization effect. See, we lost the guys. What do you call these? We got the guys. I don't know. What do you call these? The marks, face marks.
Mole.
Are they moles? I don't know. I think moles are more. I mean, these are just colors. So if you apply it, we lost it. We almost lose the eyes of the people, right? So all the details are gone. So if you do too much median filtering, you are losing lots of information, and there is a posterization effect. What is the posterization effect? You lose over smoothing, right? I don't lose the face borders, right? With this one 11 by 11 mil filter, I am losing the face borders, nose borders, and etc. With the 11 by 11 median, I don't lose the face borders. I don't lose the borders of the structure here, but things start having the same intensity value for everywhere. Okay, so those are the implementation stuff, and I will not talk about these. Okay, let me go back and let me go to the Opencv stuff. Opencv stuff, and I am going to show you the Opencv filtering functions, what we use for the filtering documentation. I think I got this here. Okay, so image filtering is here. So there is a blurring filter. This one is used for blurring the images. You don't specify the filter for the blurring, it just chooses it automatically. And box filter is just averaging filter. Okay, let's look at the documentation of the box filter. Box filter is just simply this. You can choose the filter size any way you like, and this alpha is automatically calculated. Okay, so what you do is this is your input, so image, output image. Depth is the depth of the image. Okay, it is 8-bit image or 16-bit image, 10-bit image. Okay, size is the size of the image, and normalization is when you do the normalization, it's going to choose the alpha automatically. And border type is the what should I do with the border? Should I mirror it? Should I clip it? Should I wrap around, etc.? Let's look at those bordering options actually. There are many options with the Opencv about the bordering. and let me show you them. Okay, I can do the constant bordering. Just put a constant number around. It's like same effect as clipping, only you put some values in it. Okay, where did it go? Okay, so this is a nice documentation. It just places new i's in there if constant is I with some specified I. Replicate means that just replicate, it is the replicate the, where did it go? Okay, replicate the first column with a's. Okay, last h. Reflect is the mirror reflection. Wrap around is this, you know that one. How about this reflect? Reflect is, oh okay, this one reflects but it doesn't use a. This one used the a. Transparent means, I don't know what transparent is. Some random numbers, ijk, h, ijk. I don't know what transparent is, sorry.
Maybe it can be reverse.
But I mean, I don't know, I don't see any u, v, w's, anything like that.
I mean, for example, for R, Z, for B, what reverse?
If A is 10, what would be the Z?
Z alphabetically first is A and Z is last.
If A is 10, what would be Z?
240, I guess.
So what does the alphabet has anything to do with these numbers? I don't think that what you're saying is right. What do you call it? They call it border transparent. Okay, Control F. Border transparent 5. Couldn't find it. Except border when, I don't know. I think we need to look it up. Anyway, let's go back. Okay, so this is box filter and this is how it works. Let's go back and let's find filter 2D. This is the most general one. Okay, takes the input image, takes the output image. This is the input that's going to change. This is the output, depth of the image again. This is the kernel. Okay, this is the kernel. This is the anchor point. Anchor point is, you may not, you don't want to maybe center your window around each pixel. If you don't want to do that, then use your center as a different point. But if you use -1, -1, which is the default one, okay, in that case it will be exactly the same thing as ours. And this double delta, I forgot what is delta. Optional value added to the filtered pixels before storing them on the disk. So there is, you may add some value before you store them, and border type is specified as before. If you like to use the Gaussian blurring, you don't have to use this filter 2D. You just use this Gaussian blur function. Okay, your kernel size and the sigma, and as you see, in your sigma in x and y direction could be different. Okay, good. What else can we say about it? Gaussian blur, get derivative kernels, returns the filter coefficients for computing special image derivative. Oh, okay, so this is good. So I like to apply a derivative operation to my images and calculate the filter for me. Okay, so returns filter coefficients for computing special image derivatives. So you don't have to come up with the numbers of the derivatives. You give the parameters and it calculates the derivative filters for you. Okay, good. I think although they're very interesting functions, but I am not going to spend my time on going over all of them. So you do your research, try each of them, test them. Do we have any examples? Smoothing examples? Maybe we have a Jupyter notebook. So yeah, this is a Jupyter. Okay. So the original image and averaging. This one uses filter 2D. Yeah. And see, it uses ones. 5x5 matrix. Okay, box filter. And this is the result. Okay. Same thing. Gaussian blurring is this. And this is medium filtering. Okay, good. Any questions about filtering? I think that was it. That was the end of the chapter. Okay. I am going to start a new chapter about edge detection if you don't have any questions.
I asked it before, I think, in first lessons, sorry, second lesson. These filters, Opencv filters, when I use them on an image, I wonder that if I write this function myself, how does it work? I saw that in bigger image, my functions are very slower than Opencv's. I thought it's because of C or Python. I wrote it in C, but again it didn't work. Do you know about that? Why?
What did you use to access the pixels? Did you use getXY to access your pixels?
Yes.
If you use getXY, that's going to be very slow. You should get the pixel buffer using a pointer. Use your pointer arithmetic to access the pixels one by one. If you use getXY, each XY calling is a function call, and every time when you do X and Y, there's going to be a multiplication with the row numbers and plus the column addressing and etc. So it's going to be very slow. It's the same as accessing two-dimensional matrices, two-dimensional arrays with the C. So the fast way is get the pointer to the pixel data and use the pointer arithmetic to move over your data. Even if you do that, it's going to be slower than Opencv implementation, because with the Opencv implementation, they use fast Fourier transforms to transform your images to the frequency world, and in the frequency world, doing the filtering is much faster, and you come back. And most of the time, you get the GPU acceleration with the Opencv if the GPU is available.
I didn't try that yet. Yeah, right.
Okay, so this image filtering is a very popular process. That's why Opencv or anybody else, they try to optimize it, because it is expensive. When you optimize it, things become much faster. Okay. Good. Any other questions? If there are no questions, let's start talking about the edge detection. Okay, again, these slides are from Alper Yılmaz Mübarek Shah, but well, I mean, the slides are there, but I added lots of stuff. I removed lots of stuff. I modified them, and I forgot what I did. Okay. So edge detection is this. You have an image you like to find the edges in the image. So what is the definition of an edge? Intuitively, okay, edge is the edges of the objects in the image. Okay, edges of the objects in the image. But in computer vision or image processing, okay, we don't call edges as the edges of the objects. We call the edges as discontinuities in the image. Okay, discontinuity in the image. So that means that there is a sudden change in the intensity. That's what we call the edges. Okay, for us the edges are sudden changes in the intensity, and when we find the sudden changes in the intensity, that means that we are going to find the edges that correspond to the real object edges. Okay, good. So if we look at this one, what we are going to find as the edges are going to be these, unfortunately. So see, there is this part, there is a sudden change in the intensity on my image, but these edges do not correspond to any object edges. Object edges are the ones that I draw with the green pen. Okay, this part, okay, this is an edge, this is an edge again. This one corresponds to the label on the object. Okay, so when I say edge, don't take it as a edge of the object. Okay, when I say edge, take it as the discontinuity of the image, or the sudden change of intensity in the images. That's what we mean. Okay, if you do the edge detection on this nice image, this is what would you get depending on your parameters. I don't get anything from the background, but I get lots of stuff from the image itself. If I ask a real person to give me the edges of this one, this is what would they do. At least this is what would I do. I would say, these are your edges. There is a leaf here, and this is the branch. Okay, these are your edges, I would say. That's what I would say, because I am recognizing the objects and I am trying to find the edges of the objects. Okay, so the same thing here. Very difficult problem. What are the edges? Any computer vision algorithm, image processing algorithm is going to find this. Okay, as you see, some of the edges correspond to the person, hair. Some of the edges correspond to the fence. Some of them come from the texture on this. I guess it's wood. Okay, so but we are going to ignore all those stuff. We say that an edge is a sudden change in the intensity in the image. Okay, that's what we are going to do. Edges, at edges, intensity or color changes. Okay, this is one example that kind of classifies the edges for us. When I say intensity change of the image, so what are the causes of these intensity changes? One would be the surface normal discontinuity. This is a box, this is a bottle, okay? This is the top part of the bottle. The cover of the bottle, this is the same material as this material, but their normals are different. Okay, the top part faces upwards, the side faces the sidewards, okay? So the normal, there is a normal difference between them. So there is a 90-degree difference. So when I look at this image, I see different color, different intensity. So the surface normal discontinuity causes edges for me. Also the depth discontinuity, I mean this point here and this point here, they belong to different depths in the image. So I would expect different intensities. That's what we get. Okay, the depth discontinuity edges are the most useful edges for me if I try to do the object detection using the edges. Other than that, for example, let's look at the shadow. The shadow is cast on the desk, and I know that this part will be darker than this part, and that's going to cause another the edge detection. Also the surface reflectance, surface color change, surface reflectance causes edges for me. So there are many reasons why we see edges, and I showed a few of them for you. And our purpose is to detect them using some processes, specialized processes. And we are going to see that we won't be able to detect all the edges that we like to, and there will be lots of extra edges that we detect. I don't want to detect them, but I am going to detect it, okay, as edges. So the problem is some edges will not be detectable, and some of them, even though they are not edges, I detect them, okay. That's what's going to happen. And this picture summarizes that. Okay. The ground truth edges are inside this red circle. The edge detection results are within this blue circle. So this part, the green part, is the part that I like. Green part, okay, is the intersection of the ground truth and the detected ones, okay. That part is called true positives. I like these. I like true positives, okay. False positives are the places, false positives are the edges that I find on the image, but they are not actually edges. These are called false positives. I don't like false positives. And I have false negative, which is this part. False negative. What is false negative? It is an edge on the image, but I don't find it as an edge. That's the false negative. And true negatives are the ones that are not edge, and I am not saying that they are not edge. So I like all the true ones. I like true positives, and I like true negatives, okay. I don't like false negatives. I don't like false positives. Falses are bad, okay. So once I detect all of my edges, I can come up with these numbers, precision and recall, okay. Precision is this: true positive over okay, result of method. Let's say I have found 1,000 edges, and I have found 1,000 edges, and 800 of them are true positives. Then in that case, my precision will be 0.8. Okay, that's the precision. My recall is going to be my true positives, which is 800 over ground truth. Okay, let's say there are 1/1200 of them. So it's going to be 0.6. Is that true? Whatever. Okay. Okay, so I like to have my precision and recall to be close to 1.0. 1.0 is the best, but most of the time I won't be able to get close to 1.0. Okay, so these are typical detection reporting measures, precision and recall, and I'm going to use it from time to time.
I have a question. What does it mean? Sorry, how can I say? Number of edge.
Yeah, that's a good question. Usually, when I detect the edges, I do it pixel by pixel. Okay, let's say this is a 100 by 100 image. Okay, there are a total of 10,000 pixels, right? When I do the edge detection, I would say that, okay, there is an edge, 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 edge. These are all the edges, one by one. Okay, each edge is marked by my algorithm. So out of 10,000 pixels, I say that I found 800 edges. So this is a classification problem actually. For each pixel, I say either it's an edge or not. Okay. So this is a binary classification problem. Of course, for each edge, I say other things too. For example, this one is an edge, this one is an edge, and this is the orientation of the edge. That's one thing. And the other thing is the magnitude of the edge. Okay, orientation and magnitude. Magnitude is the difference between the two sides of the edge. So if this is black and this is white, so magnitude is very large. The edge has a very strong magnitude, and orientation is 45 degrees. But I can say these two things only for the edges. For the non-edge cases, I don't say anything. Okay, good. Thanks for asking that question.
Okay. I have another question. Is it reliable measuring the edge detection with precision and recall?
Well, I mean, of course, I mean, if you like to say, how about the orientation and the magnitude? We don't report it. No, it is not perfect, but it is something very simple and it is something easy to calculate. Do you have any other suggestions?
No, not yet.
Yeah, well, there could be more ways of doing it. Do I have some results from the, yeah, okay. So this is what they do actually. They let some people do the edge detection by their hands and draw it here. Like, see, people, they did the edges, and there are, I think, 1, 2, 3, 4 different humans detected the edges. As you see, they are doing exactly the same thing as me. They are tracing the objects, the trees and the animal. If I do the same thing with the automated edge detection system, I get this. So the similarity between these two is very small, right? And this one is higher because this is a simpler picture. And this one again, because those people, they recognize the giraffes, okay? But my edge detection is not as smart as the humans. So this overlap is not that good. Okay, I guess that's it for this week. I will see you next week this time.
Thank you. See you next week.
Bye.
Thank you.
Thank you. Bye.